Welcome to the Foundry by Forge College. I'm your host, and today we are running through our absolute must-do pre-flight launchpad checks. We're going to explore the critical steps for validating deployment environment readiness. If you're building in Web3, this is an explainer you really won't want to miss.
So, in our previous lesson, we mastered the role and importance of Turbine in Solana data transfer. But let's shift gears over to the Ethereum ecosystem for a minute. How do we ensure our Ethereum launchpad is actually ready? Before we fire up our deployment scripts, we have to guarantee the environment is prepped, stable, and listening. Because if we don't, we're basically just launching blind.
Okay, let's dive right into this. Here is the literal checklist we're using to audit our systems today. We'll start with the pre-flight check, move through 3 distinct validation phases for connectivity, semantic correctness, and operational behavior. Then we'll build an automated probe, and finally lock in that readiness checklist.
Starting off with Section 1, the pre-flight check. Let's talk about validating our environments.
Think of deploying smart contracts like a literal space launch. You would never ever launch a multi-million-dollar rocket without making absolutely sure your communications tower and your GPS coordinates are fully functional first, right? Well, the exact same logic applies to our deployment scripts. Here, we see the stark difference between what we plan for and what actually happens. Designing your network gives you that expected configuration, the template. But validating? That confirms those values actually behave as expected in live operational reality.
So, what exactly do we mean by readiness? It's a collection of measurable properties that determine whether an environment can reliably accept scripted operations. By establishing this programmatic ground truth, we prevent massive gas fee losses and, frankly, embarrassing failed deployments down the line. It's our absolute safety net.
Moving on to Phase 1, connectivity. Are we even reaching the endpoint? Conceptually, this is where we ask the most basic question of all. Can mission control actually talk to the launchpad? We're talking about RPC endpoint reachability here. This means verifying your DNS resolution, checking TLS validity, establishing TCP connectivity, and timing your JSON-RPC responses. You really have to capture that round-trip time. And keep a close eye out for intermittent failures, because a repeated timeout almost always means there's a structural network problem that needs your attention immediately.
All right, Phase 2, semantic correctness. Let's see how this builds.
Okay, so we have a connection, but are we actually talking to the right place? This phase asks if our mission's GPS coordinates are correct. And that brings us to the all-important chainId. This is the unique identifier that prevents your deployment scripts from accidentally sending transactions to the wrong network. Honestly, blindly deploying a script without checking the chainId is kind of like jumping out of an airplane and only then checking to see if you actually packed your parachute. Not a great idea.
And this brilliantly illustrates what we need to look for. To fulfill our core requirements, we build a strict engineering matrix. For endpoint reachability, we test with an HTTP post, because scripts obviously can't run without RPC access. For chainId parity, we call ETH_chainId to avoid those wrong chain transactions we just talked about. And for method availability, we attempt basic calls, because missing methods will break our tooling completely. This matrix right here, it's the backbone of our checklist entries.
Which brings us to Phase 3, operational behavior.
So we have a connection and we have the right coordinates. Now we need to make sure the weather conditions around our launchpad are stable enough for a successful launch. This operational weather is influenced by several variables: gas estimation accuracy, block time stability, Explorer indexing delays, and rate limiting. In our various Forge College learning programs, we heavily emphasize this step, simply because operational quirks, like strict rate limits, will force you to add retries or exponential backoff logic right into your automation scripts.
A huge part of this is testing eth_estimate gas. It's a JSON-RPC method used to verify that the node accepts complex payloads, and more importantly, actually returns sensible estimates. Remember, consistent gas estimation issues can result in massive overpayments, or even completely failed transactions if the estimates are returning consistently too low.
Next up, Section 5, the automated probe. Let's test the environment.
You know, we really don't want to do all of these checks manually every single time. Instead, we write an automated scout drone. It's just a small script we send out into the environment right before the deployment. Our drone follows a stripped flowchart. Step 1, verify basic connectivity. Step 2, validate identity and parity. Step 3, exercise critical RPC methods. It's a very structured, step-by-step process. Developing these repeatable, reliable engineering workflows is exactly what separates a chaotic deployment from a completely seamless one.
So, The crucial point is this programmatic probe doesn't have to be complicated at all. A minimal Node.js script using native fetch is literally all it takes to confirm RPC responsiveness and basic method support. This script automatically checks the rpcUrl baseline behavior, making sure everything is exactly as we configured in our template.
Inside that script, we make a few key calls. First up is web3_client version. This reveals the client type and version. Calling this early in your probe is an absolutely essential diagnostic step. If your node starts throwing strange, undocumented errors later on, knowing the exact client version is how you troubleshoot effectively.
We also call eth_block number, which provides the latest blockhead. Crucially, you need to run this probe from the actual machine, or the CI runner that will execute the deployments. Oh, and a quick tip, it returns a hex value, so remember to convert that hexadecimal into a decimal for your human-readable checklist.
So you might see an output kind of like this, 0x5208. To put that into perspective, this number is an example of an expected hex gas estimate for a basic no-op transaction. Seeing this specific value returned from your probe mathematically proves the node can successfully process gas estimation calls.
Now, if you are running this in continuous integration, you absolutely must treat a non-zero exit as a failed readiness check. Period. No exceptions. If the script throws an error, you have to capture that exact error text and log it as a failure with a precise timestamp. We do not allow silent failures here.
Finally, Section 6, the Readiness Checklist, our final artifact. This is the final piece of the puzzle, our ultimate sign-off document that has to be approved before our rocket leaves the launch pad. To build this document, you, as the developer, need to record the exact observed chainId values, the endpoint response times, your example ethos estimate gas results, and any rate limit headers you encountered. Doing this produces a comparable, historically trackable document that your peers can confidently review.
I want to leave you with this absolute golden rule. Do not mark an environment ready without passing connectivity, identity parity, and method availability checks. If those three pillars don't hold up, the environment is fundamentally unsafe for automated deployment. Seriously, don't do it. So, the only question left for us is, are you ready to convert your completed checklist into bulletproof deployment scripts? Because in our next explainer, we'll learn exactly how to do that. Thank you so much for joining me for this session. Be sure to visit Forge College to dive deeper into this subject and explore a ton of other fascinating Web3 topics. See you next time.